Alright, in this tutorial what we're going to be looking at is a way that we can calculate the probabilities when events are independent from one another, and also we're going to move into later on when they're dependent on one another. So basically we're going to look at a situation where we might be rolling a dice and then picking up that dice and re-rolling it and finding out what the probability is of, say, rolling a 3 on the first roll and then rolling a 3 again. We're also going to look at what might happen where these events are completely independent of one another, say rolling a 4 on a dice and selecting the ace of clubs from a deck of cards. Those two events are completely independent from one another. They don't affect one another. And in that case, we can calculate the probability of them happening very simply. The other thing we can do is talk about, let's say we have a bag of gumballs and there's 5 red and 5 blue. What is the probability of reaching your hand in, selecting a red gumball, and then putting it back, shaking the bag, reaching in and grabbing a blue gumball? So what is the probability that one event will happen and another event will happen where the two are independent of one another? So that's important to say. That's with replacement when we put the object back, and when the two events aren't related to each other in terms of whether or not they are dependent. So how we do this, and as we'll learn when we're figuring this out, is that it's quite simple that we just have to multiply the probabilities together. So the equation here, and I would highlight this if I were you, has some interesting notation here. There's this little symbol here that looks like this. This symbol stands for AND. Another way, a logical AND, or intersection. And later on we'll see how it's related to something called an intersection. So what it says, what is the probability of A then B? And simply what we say is we take the probability of the first event multiplied by the probability of the second event. And this is when they're independent, right? They have no effect on the occurrence of the other. So let's say that you flipped a coin. On the first time you flip it, the probability of getting heads is 1/2. The second time you flip it, the probability of getting heads is 1/2. No matter how often you flip it, the probability of getting heads is always 1/2. It doesn't matter. Some people might say, you know, oh, I flipped a coin 1,000 times. I got a head every single time. It's unlikely, but it could happen. It's in fact very unlikely. On the next flip, you might be duped into thinking, well, I've got to get a tail since I've gotten heads the last 50 times or last 1,000 times. But that's not true. Regardless of that, you will still end up flipping, and it would be a 50-50 chance, a 1-to-1 odds, or a 1/2 probability that you will end up with heads. So it's very, very important that you understand, if the event is independent of the previous event, the probability remains the same. You could roll a dice and get a 5 10 times in a row. It does not mean that on the next roll you're likely not to get a 5, or that you're likely to get a 5. Unless, of course, somebody's played with the dice and they made it so that it's loaded so you always get a 5. But that's not a random chance. That's been manipulated. So considering the following situations, calculate the probability of rolling. We're going to roll a dice twice. We're going to pick it up, roll it. We're going to pick it up, roll it. And the first time we pick it up, the probability of getting a 3 is 1/6. There's only one outcome that's a 6. That's a 3, and there's 6 possible outcomes. On the second time you roll it, the probability of getting a 3 is 1/6 as well. Calculate the probability of rolling it twice in a row. So the probability of rolling a 3 and then a 3 is the probability of rolling a 3 times the probability of rolling a 3. I should write rolling 3, then rolling 3 like this. So it becomes 1/6 times 1/6, which is 1/36. So the probability of rolling a 3, then a 3. So that's a good way to read it, actually, is to read this word here, this intersection of the word and, read it as then. Probability of rolling a 3, then rolling a 3. is 1 over 36. Okay, so with that, we might want to look at something, calculate the probability of flipping a head and rolling a 6 on a 6-sided die, and then selecting an ace from a deck of cards. Okay, so what we're looking at here is the probability of rolling a head, then rolling a 6, then select an ace. So that's sort of a simplified version of writing that out. So what it'd be is probability of flipping a head times the probability of rolling a 6 times the probability of ace from a standard deck of cards. The probability of flipping a head is 1/2. The probability of rolling a 6 is 1/6. There are 4 aces in a deck of cards, and there are 52 cards in a deck. So that simply becomes a multiplication of those, and you should show these steps. Don't just show the final result. So I multiply the top, 1 times 1 times 4 is 4. I multiply the bottom, 2 times 6 is 12 times 52, 624. If I divide both of these by 4, I can reduce it to 1 in 156. So that's the probability. This is a small number. So I divided it and I multiplied by 100 to get it's only a 0.64% chance. So the number prior to that was actually quite a bit smaller. It was 0.0064. So it's 0.64 chance. So less than 1% chance of that happening. So, you know, if you wanted to take someone up on a bet for that, you would definitely say, yes, go for it. The odds in favor of this are very, very low. The odds in favor, if you wanted to calculate that, the odds in favor. So if you were to ask what are the odds, it would be 1 over 156, 155 over 156, which would tell us that the odds in favor are 1 to 155 in favor of that happening, or 155 to 1 against. And clearly 1 to 155 in favor means it's not likely to happen. A less than 1% chance means it's not likely to happen. And a 155 to 1 against means it's most likely not going to happen. And that's how you would read all of that. So you simply multiply probabilities. It's important that you realize this is about replacement. Okay, so I'm going to flip the sheet over to the work that you're going to do, and I'll explain some of the tasks here just so that you're very clear about what you need to do. So in the first one, it's a family wants 3 children. Calculate the probability the family will have 3 girls, given that the chance of a boy or girl is 50%. So the first child can be a boy or a girl, 50%. The second child can be a boy or a girl. Third child can be a boy or a girl. Okay. In this case here, when there's Shannon has 4 highlighter pens in her pencil case, 2 yellow, 1 orange, and 1 blue. Calculate the probability of getting 2 yellow highlighters in a row, and calculate the probability of getting a yellow followed by a blue. For the first one, when it says 2 yellow highlighters in a row, it's very important that she reaches in, selects one. Oh, look, it might be yellow. Puts it back, shakes the bag, pulls it back out. It's very important to understand that when we're talking about these independent events, in this case, we're talking about when there's replacement. Okay? It changes if we take the object out and don't replace it. Then they're dependent events, because the next probability depended on the previous probability. Okay, it depended on what you selected the first time. So right now we're just doing the independent. In the next question, question number 3, it says calculate the probability that a green tile is drawn, blah blah blah, and if you replace it and draw again. And then it says, how might it change if you didn't replace the first tile? So you select it, and then make the selection again. So it's a little bit different. Explain why these answers are different. In the next one, it says, consider the following game. Player wins if the is blue. I think you have to write this down in here. This is blue, and this is red. You can't tell on your sheet which is which. So write blue and red, and it's split right in half. Okay, so this represents half, and you can see that's a quarter and that's a quarter. Over here we've got this is broken up into sections, so you can see it's 1, 2, 3, 4. Right, just to help you out there, you can see that there's 1, 2, 3, 4, 5, 6, 7, 8 sections. So the 2 represents this little section here, the 3 represents 2 of those sections, and the 1 represents 1, 2, 3, 4, 5 of those sections. So that's just to help you. It's a little bit unclear on the sheet. So what you're going to do is attempt these problems. There's a cool little maze problem at the end here, where you have a half chance of going up, half chance of going down, half chance of going up, half chance of going down, third, and a third chance of going in those directions. These are little dragons, if you can't tell, and you got to make it to the exit. Find out the probability of making it to the exit. In the last problem, it's an extension problem. Here, each junction is as likely as the other to go through. So whenever you meet a junction, if there's 3 prongs, it's a third, a third, a third. If there are only 2 prongs, it's a half and a half. And figure out which room you're most likely to end up in. Find out the probability of landing in room A and the probability of landing in room B. Now, because there's multiple cases, you have to think about finding the probabilities and see what you would do with those cases. This is a great problem, and it sort of leads us into the next thing. So what we're going to learn after this, not today, our next lesson is on dependent events, and that's when a selection is made, there's no replacement, and the outcome is dependent on the previous choice.